the oxidation number becomes less, then it's a reduction. If the oxidation number becomes positive, then it's an oxidation. Becoming less, being reduced, yeah. Whatever you prefer, how it helps you to memorize this. Yeah, we need to speak about oxidation numbers. How far have you understood the principle or the general principle of oxidation numbers? Yeah, so somehow. Yeah. What do you know for the rules of oxidation numbers?
Your oxidation number can't be higher than the amount of spaces you have in your outer shell.
Yeah, that would mean for an element in the second main group or in the second group, what could be the maximum oxidation number be there? Yeah. +2. Yeah, it can give away only 2 electrons because it has no more than 2 electrons. Otherwise, we would open the next shell already. And this is a very high amount of energy. You need to do that. So it's basically not possible. For an element in this 16th group, what oxidation numbers could we have there? -2. Yeah, we can fill up, and there's room for more 2 electrons in the outer shell, and therefore we can get up to oxidation number -2. In the case of chloride, yeah, in the 17th main group, or chlorine, I should say, what oxidation numbers would there be possible? -1 and there are also in case of the halogens or chlorine especially, there are even more available. We can fill up until 8 electrons, having a chloride Cl-, the -1 oxidation number, but we can also rip electrons off the chloride. Of the chlorine atom up to a +7 oxidation number. Yeah, that would be, for example, in HOCl4. No, it's not Cl4. HO4 Cl. This should be it. This should be. Yeah. Perchlorate. Oxygen. Oh, no, another written. PlO4. That's more usual. Hydrogen perchlorate. There we have really a +7 as an oxidation number of the chloride of chlorine.
And that's because it's given 1 turn of hydrogen.
No, it's about the structure. We have again a tetrahedral structure. But now there are the electrons are mesomerically distributed around the oxygen atoms. And calculation-wise, the rule that oxygen has the oxidation number of -2 is applying there. So we have total -8 from oxygen coming, plus +1 from the hydrogen, leaving a -7. So chlorine, sorry, needs to have the oxidation number of +7. Yes.
The electronegativity is for the place of part.
Yeah, we can also include the explanation via electronegativity. This is electronegativity comes into play when we look at a molecule and try to distribute the electrons to figure out the theoretical electron distribution for oxidation numbers. The rule is that the element with the higher electronegativity gets credited formally all the electrons of a bond, not of the whole molecule, but of a bond, which is part of. So, like in this example, this would be the structure of hydrogen peroxide, H2O2. It's a linear molecule. And we can get from the electron from periodic table of elements, or we know already that oxygen is the bonding partner with a higher electronegativity than hydrogen. So in this case, we would credit oxygen those two bonding electrons and also those two bonding electrons. But in here between, there is a bond between two equal elements. So there is no difference in oxidation, in electronegativity. In this case, the bonding pair would be distributed equally. Now we count the electrons for each oxygen. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Oxygen has usually 6 electrons available due to its place in the periodic table of elements in the 16th group, or in the 6th main group, 6 electrons in the outer shell. And now we have 7, one more than usually. So it would mean we have a negative, theoretical negative, single negative charge on the oxygen, and this is also the oxidation number. For hydrogen, we have now 0 electrons instead of the usual 1 electron, so 1 electron less makes a positive charge or positive oxidation number on both of the hydrogens. Oh, yeah. And so you see also this is one exception from the rule which says oxygen always has the oxidation number of -2. No, not always. There are exceptions. This would be one of them. There's also an exception for hydrogen not having the oxidation number of +1. This would be in this compound, lithium aluminium hydride. This is one of the rare cases where hydrogen has the oxidation number of -1 actually. For lithium, element of the first group, an alkaline metal, there is only oxidation number of +1 possible. Aluminium, this rule maybe you have not heard so far. Aluminium has always the oxidation number of +3 without exceptions. And this now putting together, we have a +1 and a +3, summing it up, it gives us a +4. And the overall charge of the molecule is 0. There is a not charged molecule or non-charged molecule. Therefore, hydrogen needs to have the oxidation number of -1. This compound is usually used in organic synthesis, or when you're doing organic chemistry reactions, because it's a strong reduction agent. If you need something reduced in a chemical reaction, then you can easily use a lithium aluminium hydride because it's a strong reduction agent. That means itself becomes oxidized. So the oxidation number of hydrogen becomes more positive until ±0 in this case. So in reactions with lithium aluminium hydride, basically gaseous hydrogen will be produced. Yes.
Is there a rule of thumb for when the electronegativity difference between two elements is negligible and when it does start having an effect?
So when you're doing it like this, you will always have, if there is any difference, then it's a difference.
Okay.
Yeah, this is more or less a theoretical approach, but it's a very helpful approach. And for that, you say, okay, a difference. Okay, difference. There is a difference. So all electrons go to this partner. How clear are you on the terms of reducing agent and oxidizing agent? Does this need further explanation? Okay, then let's do it. Yeah, what is a reducing agent and what is an oxidizing agent? Of course, we are still talking about the topic of redox reaction, so it has to do something with that. Let's start with reducing agents. An agent is something, some compound which does something. It's acting. And the acting now depends, is directed to a reaction partner. What this agent is doing is reducing the reaction partner. So it makes the oxidation number of an element in the reaction partner or negative, positive, by reducing something. No, negative. Negative. If I reduce your income, I make it less, yeah, I make it negative, more negative. If you have a divorce, the wife is reducing your bank account. Yeah. Sorry. If I oxidize something, in the historical term was we are using oxygen in a reaction. I'm firing something up, bringing it up, make it more positive. So a reducing agent makes the oxidation number of its reaction partner more negative. This can also be from +3 to +2. That's also more negative than the starting oxidation number. It doesn't necessarily mean that they have a negative sign in front of the oxidation number. It's just more negative compared to the original state. Yes.
But that means they are gaining electrons, right?
The reducing agent now is no. Let me think. That's always to think. If I make an a reaction partner oxidation number more negative, that means I transfer electrons to it, to the reaction partner.
Just giving more.
Giving electrons to a reaction partner is reducing. This is a property of a reducing agent, you say. And by this process, when a reducing agent transfers his electrons to a reaction partner, his own electrons, of course, become less, and therefore its oxidation number now becomes more positive. Yeah. So a reducing agent becomes oxidized while he reduces the partner. And of course, the same on the opposite side. An oxidizing agent is oxidizing its reaction partner and itself becomes reduced. Just a mirroring of the same of a reducing agent. Let's look at a simple, this would be a reduction reaction, a partial reaction. Yeah, be aware, redox reactions always appear in pairs. When there is a reduction, there has to be an oxidation on the same reaction. Only reductions happening, that's not possible. Or only reductions happening, that's also not possible. But for demonstration purposes, I'm writing here now a reduction reaction alone, which would be nitrate ions in acidic environment becoming nitrogen monoxide and water. What oxidation numbers do I have here in the nitrogen of nitrate? +5. Yeah, we have -2 from oxygen, 3 oxygen, that means -6. The overall charge of the molecule is -1. So I need +5 on nitrogen to get the overall charge to -1. So -2 on oxygen. Oxidation number of hydrogen or proton? +1, of course. Oxidation number of nitrogen in nitrogen monoxide? +2, exactly, because oxygen has -2. Oxidation number in hydrogen in water?
+1.
+1. Oxygen? -2. Okay. So, where does something happen and what does happen? Looking on oxidation numbers.
So nitrogen is reduced heat. So
Yeah, let's start from the beginning. Of course, you're right. Nitrogen in nitrate starts with the oxidation number of +5 and ends up with the oxidation number of +2 in nitrogen monoxide. So, like you said already, nitrogen in nitrate is reduced to nitrogen monoxide. By how many electrons? How many electrons would be transferred in this reaction? 3. Does nitrate give these electrons away or takes it up?
takes it.
It takes it up, yeah. It takes negative charges, therefore its own oxidation number gets less. Yes,
Aren't we missing a hydrogen atom?
we are missing more. Okay, let's first put in 3 electrons. Yeah. Now then, the equation is not quite right yet. What is wrong? I think you have noticed it already.
Yes, that the matter is appearing out of nowhere.
Sorry?
That the equation is unbalanced.
It's not balanced, yeah. How many hydrogen atoms and oxygen atoms need I to balance? How can I put this?
Atoms at least 2.
Okay, then what do I have? My hydrogen balance would be correct now.
Also 2 nitrogen should be 0.
Nitrogen should be 0. What?
Hydrogen. Because it's standing there.
No.
There should be 2 nitrogen.
In this reaction, when we
On the right side, it should be 2N.
2 NO?
Yeah.
Yeah, then I would to add up 2 nitrate ions as well. So that would be a not so good approach.
Or on the hydrogen.
Exactly. Having 2 water molecules gives me 2 oxygen atoms plus 1 oxygen atoms makes 3. And also here I have 3 oxygen atoms in the nitrate ion. And of course I can easily make 4 protons to balance out the water hydrogens. And then when I also look at the charges, on the product side I see there are no charges at all. And on the product side I have a negative plus 3 negative, there are 4 negative charges, and I have 4 positive charges in the proton, so I have also 0 net charge on the EDAC side. So this would now be the completely balanced reaction of the reduction of nitrate to nitrogen monoxide. Yeah, what is here now the oxidation agent? The oxidizing agent, I have to say. What is getting reduced? The oxidizing agent is getting reduced. Nitrogen is getting reduced, but we cannot pick out nitrogen as alone in this ion. So the answer to this question, the oxidizing agent in this reaction is the nitrate ion, which becomes to follow up this question, which becomes reduced to nitrogen monoxide. So the answer, the oxidizing agent is nitrogen, is only partly correct, because the oxidizing agent is nitrate, or 100% the nitrogen atom in nitrate. Would we have a reducing agent here in this reaction? Just a theoretical question now.
The oxygen?
Where?
It's gaining electrons.
No, the oxygen is not gaining electrons. Oxygen's oxidation number is always negative. So it's not involved in any transfer of electrons. If I go the other direction, I have my nitrogen and nitrogen oxide changing from +2 to +5. So I get a more positive oxidation number in the nitrogen, and therefore this would be the reducing agent. But for that, the reaction needs to go in the other way, but it does not. This is a reaction which is at 100% on the product side. Do you have any questions for the moment on the topic of redox reactions? I think about this redox potential of metals, and so we should talk in the next tutorial, but because this is a little bit more, or I cannot explain it in 4 minutes. Let's put it that way. There was a question?
Yeah, in this equation, what is the power for bonding 3 electrons? So that to balance them.
It was we want to balance the net charge on product and EDAC side. In case of redox reactions, or reduction or oxidation reactions, we do not only need to look at the amount of the single atoms that they operate. I also need to look at the amount of the charges on each side. And of course, because there are electron transferred, they are part of the reaction, and therefore I need to write them somewhere. So in this case, I write them on the EDAC side. The counter reaction, the oxidation in this reaction would be copper. The experiment, in fact, would be copper treating with nitric acid, and therefore we get not only nitrogen oxide, but it is one of them, nitrogen monoxide, and the copper is being dissolved, copper 2+. So copper is oxidized. Copper is the reducing agent in this reaction, and there we get 2 electrons released. And then I see also, what I also see now by writing down the electrons is the oxidation reaction gives me 2 electrons, but the reduction reaction consumes 3. So the amount of electrons given and taken is not equal yet, but it has to be equal to be a chemical reaction. There are no free electrons swimming around or a reaction happening on electron credits or electron debts. Therefore, I have a simple tool of least common multiples. So I multiply this reaction, complete reaction, with 3, and this complete reaction with 2. Then I have 3 copper reacting to 3 copper 2+ plus 6 electrons, and down here I have 2 nitrate ions with 8 hydrogen with 8 protons plus 6 electrons reacting to 2 nitrogen oxide and 4 water. Now I see my electron balance between oxidation and reduction reaction now is also balanced. So this would be the 3rd dimension of balancing, if you would call it that way. First, I need to take care about the atoms, then about the charges in the reaction, and then about the electrons in account of oxidation and reduction reaction together. Okay, more questions? then I would say we made it on the point. And yeah, see you all next week. That would be the last tutorial before the winter break. So in case you have any things you are not sure about, you want to question, you want more explanation, feel free to bring. I think last session before winter break is a good time to get things straight. Yeah.
I just wanted to ask you something. Well, that's it.